Hey there, do you want to learn the ZZ method? This video is going to explain the most important and fundamental concept of ZZ method, which is called edge orientation, EO for short. So this video is going to be broken up into 4 parts. The first is explaining the amazing theory behind how EO works. The second is how to actually solve EO. The third is some examples, and lastly, I'll cover how knowledge of edge orientation can help you understand other methods like RU and CFOP. Let's get started. Let's start with 2 basic concepts. The first concept is called permutation and orientation. So when we're trying to solve a piece on a Rubik's Cube, there are actually 2 conditions that need to be true. The first condition is permutation. Permutation is the location that the piece is in. And so if we want to solve this white and red piece, it needs to belong in the location of the white and red centers. So if we move it there, then now this piece is permuted. But there's one more thing we have to do, which is to twist this edge into the correct way. And the way the edge is twisted is called orientation. So if we somehow twist it and then put it back, now this edge is solved. It's both permuted and oriented. The second concept is natural and unnatural moves. There are 6 basic face turns that you can do on a Rubik's Cube, and 4 of them belong to a category called natural moves. So these are all of your R, U, L, and D turns. These are all natural moves. And the reason they're called that is because when you're holding the cube in home grip, these are all very comfortable to do. You can access all the R, U, L, and D turns at any time. The remaining 2 moves, though, belong to the unnatural category. Why are these unnatural? These are F and B turns, and they are a lot more awkward to do, and they only work well in certain hand positions like this. So in any good speed solving method, you want to use as many natural moves as you can so that you can turn really fast. Now, you might be wondering, can't we just solve the whole cube with natural moves? And the answer is, you're really close. You almost can. This is the closest you can get with solving the cube with only natural moves. And so you can see that you can solve all of the corners, but with the edges, you cannot change the orientation of the edges. Turns out that with natural moves, it's impossible to twist these edges so that they're solved completely. It's because of the way that natural moves affect the position of stickers on the cube. So a sticker is just a colored side of a piece. So this is the red sticker, this is the white sticker. Currently this edge is twisted. And let's talk about the way that natural moves affects the position of these stickers. Let's watch this red sticker and keep track of all of the places that it is allowed to visit. So right now it's on the bottom. If we do an R move, we can see that it visits all of these places here. We do a U move, it visits all the spots on the top. L moves, goes all the way like this. And D moves, it visits all the spots on the bottom. So these are all of the possible places that this sticker can visit. And if we plot them on a paper cube, this is the resulting pattern, where all of the purple spots are these places that that sticker could visit. And these purple spots are what's forming an orbit. So an orbit is a set of stickers where if you are a sticker here on the orbit, you can only visit other places on that orbit, and you cannot go outside of the orbit. So let's just say that we wanted to twist this edge. Why can't we twist it? It's because when we say we twist an edge, it means that this red sticker here, which is currently the corresponding position here on this orbit, right? We want this red sticker to go onto the side, which is outside of the orbit, as you can see. So that means that we cannot visit that spot. No matter what we do with natural moves, we just can't solve this piece. The only way to actually twist a piece is to use to twist an edge is to use unnatural moves. So F or B moves. So for example, let's look at this red sticker again, and this is the F side, right? So right now it is on this purple orbit, but watch what happens when you do an F move. It goes here. It goes outside of the orbit. So F and B moves are the only moves that let you move stickers between orbits, in and out of the purple orbit. So now, if we try to use natural moves to solve this edge, we can. And you can see now it is in a different orientation than it once was. So yeah, F and B moves are the only moves that can change the orientation of an edge. It can flip the way that the edge is twisted, right? There are two ways that this edge can be twisted. The first way is called good orientation. Like, this is a good edge, just the way that it's twisted. You can solve it with natural moves. So that's what a good edge is. A bad edge is an edge that you cannot solve with natural moves. You have to use unnatural F or B moves to solve them, and that's why they're bad. So now that we understand how edge orientation works, let's talk about how the ZZ method works in general. So here's a scrambled cube, and we want to use as many natural moves as possible to solve the cube. But it turned out that natural moves aren't enough to solve a cube completely, and the most that we can do is get to a state like this, where some of the edges are twisted wrong, and there's no way for us to use natural moves to twist these right. So these edges are bad edges, and they are what are stopping our plan from working. The idea of ZZ is to address these bad edges at the very beginning of the solve. So here is our scrambled cube, and some of these edges are bad, and we aren't able to solve these edges with natural moves. So ZZ introduces a new step called EO, like this. So here's a new arrow here. That brings the cube to a new state where the EO is solved. That's what we call it. What EO solved means is that all of the bad edges have been twisted into good edges like this. Nothing has been actually solved yet, but now we can fully solve the cube with natural moves. So this EO step is the focus of today's video, and I'm going to show you exactly how to turn a scrambled cube into a cube where all of the edges are good. So if we want to twist all of the bad edges, so all the edges are good, we must first know what good and bad edges look like. And we'll find these rules to identify them. But first, one thing to note, which is that the way that you are facing the cube actually changes whether edges are good or bad. And the reason for that is whether an edge is good or bad depends on whether it is solvable with natural moves or if you need to use unnatural moves. Unnatural moves here are these F and B layers, like this. But as soon as you hold the cube a different way, those same layers become L and R. So you don't want to change the way you're holding the cube during edge orientation, because that might change which edges are good and bad halfway through. So we want to use the same color center on the top and the same color center on the front. In this case, we'll use yellow and blue. With that out of the way, let's talk about what makes a good edge good. So, okay, this EO state has everything good. Why is this green or yellow edge good exactly? Well, because you can solve it with natural moves, like with the U2, right? Like that. But there's a special property that we talked about in the theory section where when you are using natural moves to solve things, the stickers on the purple orbit will stay on the purple orbit, right? So right now, the sticker that is on the purple orbit currently is this yellow sticker. And when the sticker is solved, when this piece is solved, that sticker is still on the purple orbit. So that makes perfect sense, right? So good edges must have that sticker, that special sticker, on the purple orbit to begin with, so that they're on the orbit at the end when they're solved, right? And let's look at an example where that edge is bad. So here's a scrambled state where some of the edges are bad. The same green-yellow edge, why is it bad? Because that sticker that belongs to the purple orbit at the end, that special sticker is outside of the purple orbit currently. They're here. So you cannot use natural moves to get this from outside the purple orbit to inside the purple orbit. So in other words, those special stickers that are on the purple orbit at the very end, you must start them on the purple orbit, and that's what makes a good edge good. Bad edges do not have that sticker on the purple orbit to begin with. So let's come up with a name for these special stickers. Let's call them key stickers. And let's have some rules so you can identify what key stickers are. So every edge has a key sticker, and there's two categories. For the edges that are on the top or the bottom, you can very obviously see that their key stickers are top or bottom colors, like that. So that's how we come up with the first rule for key stickers. If an edge contains the top or the bottom color, its key sticker is the top or bottom color. Okay, what about the edges that are in the middle layer, like these, that do not contain either the top or the bottom color? What's their key stickers? Those key stickers are either the front color or the back color, like that. So that's how we get the second rule, which is for the edges that do not contain top or bottom, its key sticker is the front or the back color. Okay, so now we can say that good edges have key stickers on the purple orbit to begin with. Bad edges have key stickers outside the purple orbit. And let me give you some examples, because this is a concept that relies a lot on recognizing patterns, and at the beginning it's going to be kind of hard. So I have a cube where I blanked out most of the pieces, and let's hold it with yellow top, blue front. And so we have 4 edges. Let's look at the first one, which is this white and red edge. So its key sticker is the white sticker, because according to rule 1, if the edge contains the top or the bottom color, in this case the bottom color, that's the key sticker. And right now, it is on the purple orbit, like this, right? So that's a good edge. A bad edge is something like this, where its key sticker is this yellow here, because it contains either the top, in this case the top, or bottom color. That is outside of the purple orbit right now. It's here. So that's a bad edge. And for edges that do not contain either the top or the bottom color, its key sticker is either the front or the back, depending on what it is, what it has. So this red-blue edge has blue, and that's a front sticker, front color. So its key sticker is this, and it's good. It's on the purple orbit. This edge is bad. Well, clearly it's because it's flipped, but most importantly, that key sticker is green, because that's the back color, and it's not on the purple orbit. So yeah, those are some examples of good and bad edges, and I think it's a good idea to practice these. So on the screen right now, I have a scramble that you can follow along. So you can scramble your cube with the white center top and the green center front. And once you're done scrambling, you can rotate it like this. So we have this orientation, and then you should figure out on your own which edges are good and bad. So you can pause the video and come back. Here is the answer. I've marked all of the bad edges with pieces of tape. There is a bad edge here at the top. In the middle layer, we have these 3 bad edges, and at the bottom, we have 2 bad edges. So great, now we know how to identify good and bad edges. How do we solve them? So remember from earlier that the only moves that can change the orientation of edges are F and B moves, the unnatural moves. So if we have a good edge like this, if we do an F move, it becomes bad. We do another F move, this bad edge becomes good again. And the reason is that the key sticker that is supposed to be on the purple orbit when an edge is good, it gets moved out of the purple orbit, like this, and then it becomes bad. And do another F, then that bad becomes good. It moves back into the purple orbit. So that's how F and B moves affect edges. Good becomes bad, bad becomes good. So how do we use that to solve bad edges? The strategy number 1 is to eliminate 4 bad edges by placing 4 bad edges on the front layer or on the back layer. It works the same way. So once 4 are on the front, you do an F move and then they all become good edges. Okay, so we need to move 4 bad edges onto the front, and we need to use natural moves, because if we do any F or B quarter turn moves, then that will mess up the orientation of edges and create new bad edges. So let's move this bad edge to the front. There's already one here. Let's move another bad edge to the front, and notice that we're all using natural moves, just like U, L, and then D moves. Now we have 4 bad edges on the front. We can do any direction quarter turn F move, and then you can check that all of these have become good. So we have just eliminated 4 bad edges, and I can just peel off these stickers. So, okay, we can eliminate 4 bad edges at a time. Is that enough to solve EO? Sometimes. So let's say if you have a multiple of 4 bad edges, so for example 4, 8, or 12. If you have 12 bad edges, you can reduce the number of edges by 4 to 8, and then from 8 to 4, and then you reach your goal like that. Just repeat the steps over and over. But what if you have a not multiple of 4 number of edges? So for example 10 bad edges. You can repeat the same thing where you can eliminate 4 bad edges and then do that again until you reach 2 bad edges. What do? How do you turn 2 bad edges into 0 bad edges? And the answer is strategy number 2. So if you have 2 bad edges, I'm going to show you how you can turn that into a 4 bad edge case, so then you can eliminate 4 bad edges as usual. So back to our example, remember that we just eliminated 4 of the 6 bad edges. There are 2 at the back waiting to be solved. So the way to turn this into a 4 bad edge case is to move one of the bad edges to one of the layers, F or B. In this case, let's just choose F so it's easier for you to see. So now it is on the F layer, and only one bad edge is on the F layer. Do any F quarter turn, so let's say an F prime. And what happens is the 3 good edges here turn bad, and that bad edge becomes good. So we have just created 3 new bad edges in addition to the one that's still at the back. So now we have 4 bad edges. Okay, so now we have a 4 bad edge case, and we just need to move this one to the front. But it's kind of a hassle, and it would be nice if we could just do an F2, so that we can then fill in this gap with the bad edge, and then we can do F. So the reason why we're actually allowed to do F2 and B2 moves when we're moving around these bad edges is because F2 and B2 don't change edge orientation. So remember how if an edge is good, you do an F, it's bad, and then do an F again, it's good. The same thing happens to bad edges. So good becomes good and bad becomes bad, nothing changes. So you are also allowed to do F2 and B2 moves. Okay, great. So now we can update the stickering again because we just solved EO. And next up is going to be an example solve so you can see the complete process. So here is a full example solve on how to do the EO step in ZC. You can follow the scramble on screen with white top and green front. Then you can flip around the cube like this. The first step is to look for bad edges. So we'll start from the top and work our way down. This edge is a good edge because its key sticker is this yellow sticker right here, and it's on the purple orbit. If you need a quick reminder of what those are, this is the rules of key stickers, and this is what the purple orbit looks like. These top stickers bottom stickers, front 2, and back 2. Right, so this is a good edge. This is also a good edge because the key sticker is on the purple orbit. This is also a good edge because the key sticker is here. Bad edge, key sticker. So I'll put tape on the bad edges so we can keep track of them. Just for the purpose of this tutorial, this is a bad edge. I'm just going to go more briefly now. That's a bad edge. That's a good edge. That's a bad edge. Good, good, bad, and bad. Great, so now that we recognize their bad edges, it's time to solve them. In total, we have 1, 2, 3, 4, 5, 6 bad edges. So last time I showed you how to move those bad edges to the front. This time let's try the back side. So in this case, we already have 2 bad edges at the back. So we can add a third edge here. So we can do a U, and now there's 3. And then we can add a 4th bad edge by doing an R2, like this. So now we have 4 bad edges on the back. We can do, let's say, a B move, right? It doesn't matter which direction as long as it's a quarter turn, and those bad edges all become good. Just a moment. Alright, I updated the tape, and now there's only 2 bad edges left. So to turn 2 bad edges into 4, we first move one of the bad edges to either the front or back layers. Oh, it's already here? Great. So we can do, let's say, an F move, and that will turn this bad edge into a good edge, and the 3 that were good are now bad, like that. Okay, so here we want to solve it normally with just 4 bad edges, and there is 2 options. The first is what I showed you, where you can do an F2, so you can kick this good edge out and replace it with a bad edge, right? So now all 4 of these are bad edges. Another option is to not do an F2 and instead kick this bad edge out with another bad edge and then move it back to the F layer like this with a U prime, right? It does the same thing, and we all have 4 bad edges here. And those are just different strategies you can use. Regardless, you can do just an F move, and now all of these 4 bad edges turn into good edges. And now EO is solved. Okay, so you might have some questions. The first question is, how on earth do you keep track of all of the bad edges during inspection? And the answer is that it's kind of a skill, and it will take some practice. If you give it a couple of days, you'll be better at it. But there's also some more useful practical tricks I can give you. So when you're getting started, you can just like put your fingers all over like the bad edges, if that helps. You can also draw shapes, like you can just memorize this face is filled with bad edges, here is a triangle, and then these 2 edges are like opposite diagonal things, stuff like that. And also, if you have a really bad case, like this 10 bad edges example, you can actually forget about the bad edges and focus on the good edges, because if there's more bad edges than good edges, let's say 8, 10, or 12 bad edges, you can just choose to focus on the 4, 2, or 0 good edges respectively, and that will just make it a ton easier to plan. So another question is, okay, so you've solved EO, that's great. What's next? So in the next section, I'm going to talk about the different flavors of ZZ, so what you do after the EO step, as well as learning about how this knowledge of EO can help you understand CFOP and RU. So how is EO useful in ZZ, and what do you do after EO? So EO cross is the modern flavor of ZZ, which kind of resembles CFOP, where EO is an extra step in front of cross F2L and last layer that makes all of the other steps better. So let's do EO cross. Once your EO is solved, you can solve your cross just like with CFOP, but you use moves that don't disrupt EO. So that's natural moves F2 and B2. And what we're left with is F12 where we only need to use natural moves and no rotations. So that's the advantage. We can do something like this. Yeah, so that's pretty nice. The advantage is ergonomics, it's rotationless, and some of the annoying CFOP F12 cases disappear because there are no bad edges. And then its last layer, and you'll notice that we'll always get a cross on top OLL. And these are generally one of the better OLLs. So we have anti-soon into Y-perm. So that's pretty cool. But because there's fewer cases in general in both F12 and last layer, this enables us to use tricks that are usually reserved for lucky cases in CFOB. And now these are more likely and more worth learning. So for example, if you notice that we inserted our last pair in F12, what we could have actually done is, because all the edges are oriented, always in ZZ, you can insert it like, so that's winter variation, and that skips OLL. And perhaps the most important advantage of ZZ is that it unlocks one look last layer. Because all the edges are oriented, we get to use a alg set called ZBLL. It's an alg set that solves everything. So it would look something like this. I don't use full ZBLL, but yeah, it's a large alg set and you can learn it, and it's very fast. Another option is called EO-line. EO-line is where you solve the EO plus two edges on the bottom in a line shape. So this is the original vanilla flavor of ZZ, and nowadays it's most commonly used for one-handed solving. So it gives us a lot more freedom to block build pieces. With EO cross, you have to solve pairs like this. But in EO-line, you get to block build things like this square. There's just a lot more freedom. And this allows us to be more efficient and use less moves. But the trade-off is you don't get to turn as fast. EO can help us understand how CFOP works and why it uses rotations a lot. So I said that every good speed solving method should use as many natural moves as possible, right? So let's take this green-red F12 pair that we want to solve in CFOP. So one problem is if we try to use natural moves right now, we can't solve this pair, no matter how hard we try. Even just the edge, we can't solve it. And that's because this edge is bad, using the exact same recognition from ZZ. This is the key sticker, and it's outside the purple orbit. So how does CFOP address this? Well, CFOP is smart and says, okay, so if you need this unnatural move, let's say an F move, to orient this edge, what if we just hold the cube a different way, right? Because remember, the way that you're holding the cube changes which edges are good and bad. So this was an unnatural move that we need to use to orient this edge. Let's just hold it so that now it's a natural move. It's on the right. So now we can easily insert this pair with natural moves. So this is useful in two different ways. The first way is to tell whether you need to rotate for a pair or not. Generally, what you can do is, let's say if you want to solve this green-orange pair, you can look at the edge and see if it's good or bad. If it's good, that means you can keep the way you're holding the cube and then solve it with natural moves. We can solve this to the back, like this. But on the contrary, let's say we wanted to solve this pair next. This edge is bad, so we can't just use natural moves. The best thing to do is to rotate, and then we can use natural moves, and now the edge is good. And another more niche use case for EO detection in F2L is pair awareness. So let's say we wanted to solve two pairs, this pair and this one, right? So this is a good edge, and this is a bad edge. Generally, you'd want to solve the good edge first. So something like hide this corner and then solve this. And then you can rotate for this pair. So something like that. So in total, you only needed one rotation. But here's the exact same scenario, but we decided to solve this other pair first, the bad pair. So we need to rotate to make this bad edge good, and then we can insert this pair like that. But oh no, when we rotated, we also made the second pair bad. So we need to rotate again to solve it like this. So sometimes being aware of the EO when you're doing F2L can help you do things more smartly to avoid rotations. But how does Roo deal with bad edges? So what's interesting about Roo is that it also has an edge orientation step like ZZ, where you have bad edges that you need to twist into good edges. And this happens at the beginning of LSC. But it uses slice moves. So slice moves like this, M prime, U, M. And that solves this arrow case, that's what we call it. So how exactly does M moves or slice moves affect EO? Well, M, like M prime, is just a shortcut for doing L R prime and then rotate like this. So what we're actually doing when we do M prime is we do these moves and then we bring the F center to the top. So if we ever needed to do an F move to, let's say, fix these 4 bad edges at the front, right? You can just do this to bring the F center to the top, and then we can execute an F move like it's a U move, like that. And then these edges are oriented now. So yeah, just to repeat, it's the same thing as doing L R prime and then F and then L prime R. It's a shortcut. And Roo also has a really interesting thing for a second block where, remember how with the CFOP example we had this F12 pair that we couldn't solve with natural moves unless we rotated. The equivalent in Roo second block is something like this. In this stage, we don't actually care what the centers are. So the centers are really meaningless where they are. What's important and what stays fixed in position is this first block. So we can actually define edge orientation relative to this first block. We can say that this is the front color, the back color, this is the bottom color, and then the top color is whatever's opposite to this, which is yellow. Okay, so in this case, M moves actually changes the orientation of edges. Let's say that this is a bad edge because we can't solve this with natural moves. So we can do a wide R, and that includes an M prime move, right? A wide R. And what happens is that the key sticker here, which is blue, it used to be outside of the purple orbit, right here. As soon as you do an M slice move like this, now that key sticker goes into the purple orbit. So now this edge is good. So to solve this pair, you can do that. That's pretty nifty. Now you've reached the end of this ridiculously long video. It's the most in-depth ZZ-EO tutorial with a novel explanation. The theory behind EO lets you understand ZZ and even other methods. Thanks for watching.